This is the second video in a series where we're trying to see how the boiling point and freezing points of a solvent change upon addition of a solute. Now, the last part of the prior video has shown you that the way that you can relate the change in the boiling point to the concentration has this form. And this is something that is very nice because the parameters of this expression are well known. That is that here you only have the vaporization enthalpy, and those are numbers that are actually known for solvents, right? Now our task in this video then is try to reorganize this in a way that actually allows us for a really easy calculation of the explicit change in the boiling point, right? So we would like to have an expression that has just a change in the boiling point as a function of potentially the concentration of that solution. Alright, so let's see how we do that reorganization. First, let's start with the left-hand side of that expression, natural log of x of a. Now, colligative properties are those that depend on the amount of solute, but not on the type of solute, right? So, because we're looking for a dependence on the solute, somehow we have to change this from depending on the concentration of the solvent to depending on the concentration of the solute. But that can be very easily done because this is simply a binary solution, which gives you this, right? Well, very good. So that changes the equation from depending on the solvent to depending on the solute, but this doesn't look any easier than that. Now, it actually turns out to be much easier because it turns out that if the concentration of B is quite low, okay, so if this mole fraction is quite low, it should be a number of about 0.01, 0.02, maybe up to 0.05. It turns out that there's an approximation to solving this, which is simply minus x of b. Okay, and this is something that you can test in your calculator and convince yourself that that approximation is valid. Okay, and this is actually very simple because that's simply the mole fraction of the solute. So that is the left-hand side of the expression. Now, what about the right-hand side? For the right-hand side, what we can do is take a look at that parenthesis and see here if we can do something about it. All right, so notice that what we can do is simply just multiply through and find out that that parenthesis is just going to be equal to t sub b minus t sub b prime over t sub b prime t sub b. Okay, that is something that you can do in that parenthesis. And now we invoke an approximation, and that is to say, look, the boiling point when you add solute to that solvent is going to change only slightly compared to the boiling point when pure. And when you do problems, you will see that this change to the boiling point is actually a fraction of a degree for very low concentrations, right? So the change in the boiling point is not going to be 10 degrees or 20 degrees at all. It's going to be a fraction of a degree, maybe 1 degree and a little bit. But what I'm trying to say is that these numbers are actually quite similar. And if that's the case, then a good approximation that you can use here is this one. Simply say that the product of those two is just going to be the square of each one of them, or of either one of them, right? And in this case, we use just the boiling point of the pure solvent because those are known. Okay, so that's nice. Now, something that we can do here is to recognize that in the end, what we actually want to do is just calculate the change in the boiling point, and that is the final boiling point minus the initial boiling point, or the boiling point when pure. And that is exactly something that we have here, but backwards, right? So we can simply reverse that numerator by adding a negative sign and have the delta TB right there, okay? TB squared. And this negative sign that has appeared here is actually convenient because we also have a negative sign in the left-hand side of the expression, so that is going to allow for convenient cancellation of those negative signs. All right, so let's see if we can then reformulate this that we have right there. That is going to be x of b now minus is going to be equal to minus delta vaporization enthalpy for the solvent over R, and then you have in that numerator TB prime minus TB over TB squared. Okay, so those negative signs cancel each other out, and then we're ready to go. Okay, so that's nice. As a matter of fact, now what we can do is just solve for the change in boiling point, which is our final goal for this, and we can be ready, right? So now we're solving for that. So TV prime minus TV, that's the change in the boiling point, is going to be equal to R, boiling point of the pure solvent squared, times the mole fraction of B, divided over the vaporization enthalpy. Okay, so again, a very, very simple expression, as you can see. There's going to be one final twist to this, and that is to recognize that when we work in the laboratory, we very rarely express concentrations in terms of mole fractions. Mole fractions are really useful in theoretical work and in physical chemistry because they tell you the relative amount of molecules of one component to the other. Right? In the laboratory, we much rather prefer to have molarity or molality. So in the remainder of this video, the only thing that we're going to do is simply change that into molality, which is something useful. But that is actually not difficult to do at all. Right? It turns out that the XB, notice that this is simply the number of moles of B over the number of moles of A plus number of moles of B for a binary mixture. But if B is minority, right, so this, if this amount of solid that you're adding is very, very small, then you can neglect the number of moles of B compared to the solvent. Yes, because the solvent is going to be much more prevalent than the solid, right? So we can do the following. Natural number of moles of B over number of moles of A. Now the number of moles of A can be simply obtained as the mass of A divided over the molar mass of A. Okay, and we can rearrange this by simply noticing that this is going to be the molar mass of A moles of B over the mass of A. Okay, this is a term that we know. That is the moles of the solute over the mass of the solvent. That is just the definition of molality, which we call B of B. Right, so we've been able to find then an expression for the mole fraction as a function of molality. Right, so that expression now is going to be equal to just R TV squared molar mass of A, the solvent, divided over the vaporization enthalpy of the solvent times the molality of B. Alright, so that is going to be our final expression. We're just going to consolidate it a little bit. We're simply going to say that the change to the boiling point in a solution when you add a solute is simply a constant that we're going to call the K sub B, that is called the ebullioscopic constant, or the boiling point constant, times the molality of that solution. Notice that even though the last couple of videos have been a little long with a long derivation, the final expression is actually so straightforward and very nice. There is a linear dependence between the change in boiling point and the molality of the solution. And that dependence has to do with this ebullioscopic constant, which we can write with K sub B being equal to this. Okay, so let me write that again. R boiling point squared molar mass of the solvent over the vaporization enthalpy of the solvent per mole. Okay, so again, this is going to be extremely easy to use in problems. And again, it's still nice to see how the thermodynamic background of that expression is. Now, this is an expression that tells you the variation to the boiling point, right? So the question is, well, what happens to the freezing point? Well, to the freezing point, you will have an analogous expression, right? So delta Tf is going to be equal to a different constant, which in this case we're going to call K sub F. That is going to be the cryoscopic constant, or the freezing point constant, multiplied by the molality of B. Now, the only change to that cryoscopic constant with regards to the ebullioscopic constant is this, that instead of having the boiling point up here, you will have the freezing point, and instead of having the vaporization enthalpy in the denominator, you're going to have the fusion enthalpy, right? So that would be RTF squared molar mass of A divided over the enthalpy of fusion, which is the phase transition between the solid and the liquid. Okay, but for the rest, it's the same. One final point of importance here. Notice that the boiling point goes up and then the freezing point goes down. Okay, so notice that in principle, if you say that this is the final freezing point and that is the initial freezing point, then the change to the freezing point should be negative, right? And you have to be careful with that. What that means is that when you define these changes to the boiling point, you want these numbers to be positive. And what that means is that when you're looking at the boiling point, the final boiling point has to be larger than the initial boiling point. And when you look at the change to the freezing point, the final boiling point is going to be lower than the initial boiling point, right? So notice the switch of what is final and what is initial in these expressions, so that those delta t's are always positive. Okay, so again, notice that when you do this, you have to be careful, right? This is going to be the freezing point of the pure solvent minus the new freezing point, but this is going to be the new boiling point of that solution minus the initial, the initial boiling point. Okay, so make sure that you guys practice this in the problems. Alright, so this is the end of this couple of videos with the change in the boiling point and the freezing point of a solution when you add a solute to it.